Hello everyone, this is Vinolia Laina R, a student from Savita Engineering College. I'm pursuing my BTech in Artificial Intelligence and Machine Learning. So today I'm here to discuss and present about a very important topic in linear algebra, which is QR decomposition using Gram-Schmidt method. We'll further discuss about this method and the importance of this Gram-Schmidt method in the further slides. So let's move on to further slides. So in this slide, I'm going to be talking about QR decomposition using Gram-Schmidt method. So this is a fundamental algorithm in linear algebra that helps us to decompose any given matrix. It is usually denoted as A into two special matrices. So an orthogonal matrix and an upper triangular matrix R. So orthogonal matrix is denoted as Q, and the upper triangular matrix is denoted as R. So QR decomposition is widely used in numerical analysis, optimization, and solving systems of linear equations. So in this presentation, I'll explain how Gram-Schmidt process helps achieve the decomposition step by step. Okay, so next slide. So now let's understand what the Gram-Schmidt method actually is. So the main purpose of this method is to transform a set of linearly independent vectors into a set of orthogonal vectors. That means all new vectors are perpendicular to each other and each has a unit length while still preserving the original span of the vectors. So the process works by taking the original vectors and symmetrically removing their projections on each other. This ensures that each new vector we create is perfectly perpendicular to the previous one. As a result, we obtain an orthogonal matrix Q and an upper triangular matrix R, such that our original matrix A can be written as the product of Q and R, or simply A equals Q times R. So the next slide. Next, let's look into the mathematical foundation behind the Gram-Schmidt process. This method follows three main steps. Step 1 is the initial vector. We start by taking the first column of a matrix A and we call it U1. This becomes our initial vector that we'll use to begin the process. Step 2 is orthogonalization. For every new vector that comes after, we remove its projections into all the previous orthogonal vectors. This step ensures that each new vector we form is perpendicular to the earlier ones. And we finally step 3 is normalization. Once we have orthogonal vectors, we convert each one into a unit vector by dividing it by its magnitude. So this gives us the orthonormal vectors, which together form the columns of the Q matrix. Okay, so the next slide. So on this slide, we see the key formula used to compute the orthogonal component of a vector. For the ith vector, we subtract the projections of that vector onto all previously computed orthonormal vectors. So this process is the part of a Gram-Schmidt method organization. So which helps us to build a set of orthogonal vectors from a linearly independent set. So this projection formula shows here we can calculate how much of one vector lies in the direction of another. It is a powerful tool for simplifying complex vectors, relationships, and is essential for understanding how data behaves in high dimensional spaces. So this slide provides an overview of algorithm's implementation process. We start by initializing the matrices Q and U, both of which have the same dimensions as our input matrix. Next, we process the first column by setting it equal to the first column of A and then normalizing it to form the first column of Q. After that, we iterate through the remaining columns, applying the Gram-Schmidt orthogonalization process. So this ensures each new column an orthogonal to the previous ones. Finally, we compute the R matrix, which each entry is calculated using dot products of A and Q, giving us the upper triangular structure. So next slide. So in the sixth slide, here we can see how the code is structured. The first part, matrix initialization, sets up empty matrices like Q and R, matching the dimensions of A. In first vector processing, we assign the first column of A to U and then normalize it to the form of first column of Q. This sets the foundation for the orthogonalization steps that follow in rest of the algorithm. So let's see the next slide. So basically, this slide shows the core loop that performs the orthogonalization. So this is very important in this process. So for each new column in A, we start by copying it into U and then subtract the projections of this column onto the previous Q vectors. So this step ensures orthogonality by removing any component in the direction of earlier vectors. So after these projections are removed, we normalize the result to get the next column of the Q matrix. So essentially, this loop is where the Gram-Schmidt process happens. So this is the main part where the process actually takes place, and this is a very important step um to include the Gram-Schmidt process. So in this eighth slide, once the orthogonal matrix Q is obtained, we should construct the R matrix. The R matrix is the upper triangular matrix, meaning all entities below the diagonals are zero. So each entry, that is R of I, comma j, is computed using the dot product between the column j of A and the column I of Q. So this ensures the decomposition properly that multiplying Q and R reconstructs the original matrix. So this is the part where the matrix construction happens in the Gram-Schmidt process according to the code given. Okay. So these are the example output analysis. So here an example showing the output matrices of a simple input. The Q matrix is orthogonal, meaning its columns are perpendicular unit vectors. As I said before, the perpendicular unit vectors, we can see the computed columns listed on the left. The R matrix shown on the right is the upper triangular and contains the projection coefficients that relates A and Q. So the one in the right is the R matrix, which is also called as upper triangular matrix. So the diagonal entities correspond to the norms of the orthogonalized vectors. So this is an example output of our analysis. Okay. So this is the last slide, applications and benefits. Finally, let's look into the where the algorithm is useful. First, numerical stability. QR decomposition provides more stable ways to solve linear systems compared to direct inversion. Second, it's a key to solve least square problems, which are common in data science and regression analysis. And third, it plays a crucial role in eigenvalue problems, forming the foundation for algorithms used to compute eigenvalues and eigenvectors. Overall, QR decomposition is both mathematically elegant and practically powerful. And with this, our presentation ends. Thank you.